Well, thank you for the introduction. Thank you all for being here. And it's very nice to be here in Bath. Um, I'm going to talk about dimension dependence of critical phenomenon percolation. So I want to just start really right from the beginning. And we'll move fairly quickly because I also want to get to new stuff. But hopefully I'm going to bring you all on board. I should say throughout, we have a lot of time. So if there's anything that's not clear or if you have a question, please don't hesitate to ask. We'll try and keep things informal. Okay, so I'm going to be basically exclusively talking about Bernoulli bond percolation. So the most basic version of this, we have a graph, G, has vertices and edges. I'll always assume that the graph is countable. Of course, this will always be the case, but keep things well defined. So I have a countable graph, and we have P, a parameter. And what we do in bond percolation is we flip a coin independently at random for each edge of the graph, right? So we get this measure, which is the law of the random subgraph in which each edge is included independently with probability P. Okay, so we call the edges that we include, we call these open edges, and deleted edges we call closed. Okay, and we're mostly interested in the geometry of clusters, meaning connected components. Okay. This is Bernoulli bond percolation. Let me just briefly say that, Bernoulli just means independence, right? Has nothing to do with really the mathematician or any of the mathematicians, Bernoulli. Bond means edge, so they're just synonyms. So if we're to discuss Bernoulli site percolation, that means you take a random set of vertices instead of edges, and then you take the induced subgraph, and most things we discuss are very similar for site percolation. Sometimes the proof techniques can be slightly different, but generally speaking, you have the same techniques for both models. Okay. So the purpose, there are many things one can study with in percolation. In this course, I'm going to be basically exclusively concerned with critical percolation. So I have to first define the critical point. So let's see if G is infinite, we define PC of G, which we'll normally just write PC and leave G implicit, to be the infemal value of P such that an infinite cluster exists almost surely under this measure. Okay, now the existence of an infinite cluster is a tail event. If you change the status of any finite collection of edges, it doesn't change whether you have an infinite cluster or not. So this is equivalent to just saying that it has a positive probability, right? By Kolmogorov 0-1 law. Okay. So the first kind of basic theorem about percolation that probably many of you are familiar with, which is kind of the theorem that makes the model interesting in some sense, is that for PC of ZD, so here I mean the standard hypercubic lattice, right? So you have the vertices are the d-tuples of integers, and the edges are pairs of integers which differ by 1, plus or minus 1 in one coordinate. This is strictly between 0 and 1 for all d at least 2. Okay, now in one dimension, the model is just very degenerate. So, if you just have an infinite line, as long as you're deleting any edges, you're never going to get an infinite cluster because, if you look from the origin, you have two directions you can go to infinity. Every time you come to a new edge, it has some constant probability of being closed independently of everything else you've seen. So, you just trivially don't have infinite clusters, except when P is 1, of course, when you're keeping every edge. But once you get to dimension 2 and higher, you do have a phase transition. Okay, so let's start things off by proving this. So the first lemma we'll do is to say if G has a max degree big delta, then PC of G is at least 1 over the max degree minus 1, which is positive if G has bounded degrees. Okay, in particular, the hypercubic lattice has finite degree, so this shows that PC is positive. Okay, so the positivity of PC is just something that's true for any bounded degree graph, nothing to do with the particular geometry. Okay, why is this true? So we're just going to count paths. So here's the idea. So fix your favorite vertex in the vertex set, right? And if we want to prove that, if P is strictly less than this, then you don't have an infinite cluster. Now, of course, the probability that there exists an infinite cluster is 0, if and only if the probability that any particular vertex belongs to the infinite cluster is 0, right? Because it's countable union, right? So it suffices to prove, given that this vertex was arbitrary, suffices to prove that the probability that the origin is connected, that this vertex O is connected to infinity is 0 for all P strictly less than this. Okay. How do we do that? Well, here's a fact. Which is very easy to prove. It's a basic compactness thing. It has some fancy name that logicians use that I can't remember. Maybe someone in the audience knows. That if you have every infinite locally finite connected graph has an infinite path, starting simple path. So simple, I mean, you don't visit the same vertex more than once, starting at every vertex. Okay. This hopefully you find this a pretty obvious fact. I mean, the point is, it's not true, of course, if the graph's not locally finite, right? You can have a star of infinite degree, something like that. But for a locally finite graph, it is true, and it's an exercise to prove it if you haven't seen it before. Okay, so what this means for us is that it suffices to prove that the probability that there exists a simple open path of length at least n from 0 goes to 0 as n goes to infinity, right? If there exists an infinite one, then there exists one for every n, so it's just continuity of measure, right? Suffices to do this. Okay, now how do we do this? Well, we'll just use Markov's inequality. So we'll say this is smaller than the sum over n Actually, let me not write down. So if I have one specific simple path starting from the origin, what's the probability that it's open? Well, it's p to the n, right? So this is bounded by Markov's inequality by p to the n times the number of simple paths from the origin, right? And now we just need to bound this. Well, this is pretty easy. So we can just think, well, how many choices do we have at each step? Well, at the first step, we're at some vertex and we have, the degree, which is at most capital delta, right? And then at every subsequent step, we're not allowed to go immediately back where we went, right? So, of course, just for showing PC is positive, this optimization is irrelevant, but let's just do it anyway. Right? So this is just bounding the number of simple open paths by saying, okay, the first step you have most delta choices. Every subsequent step you have at most that -1 because you don't want to immediately go back, right? In fact, on a tree, this is actually this really is the number of simple paths, and in fact, PC is 1 over delta -1. Okay, so what we see is that if P is strictly less than this, then this goes to 0. Right, because I have two exponentials, there's a competition between the constants. Okay, is that clear? Okay. So this hopefully everyone follows. Okay. So the point is basically that the positivity of PC is something that you get essentially for free. I mean, this is maybe like the most naive argument you could think of for analyzing percolation. Whereas, PC being less than 1 is a more subtle matter. It's not just going to be a case of path counting. I mean, sometimes you can prove it by path counting. I mean, you would need to do some kind of second moment argument, right? Because, Markov's inequality goes in the wrong direction, so you need to maybe use Chebyshev. There are settings where you can do that. That won't be how we'll do it now. So what we're going to do is to use an argument due to Rudolf Peierls. So I think this was from the 1930s. So it actually predates the study of percolation. Peierls was working with the Ising model. Actually, I won't go into the Ising model in this course, but many of the things that I'll talk about, if you do have some familiarity with the Ising model, or if it comes up for you at some point in the future, just know that there are a lot of similarities between what we'll discuss between percolation and many other models of statistical mechanics. So another one you can keep in mind is self-voiding warp. And it's kind of an interesting history. So the Ising model is a model of the phase transition in magnets. So if you have a piece of iron at room temperature, if you expose it to a magnetic field, right, it remains magnetized when you take the field away, right? You can have a magnet, you can stick it on your fridge or whatever, right? A piece of hot iron no longer has that property, and there's in fact a phase transition in some ways quite analogous to the percolation phase transition that goes on as you cross a critical temperature called the Curie temperature, a rare case of something being named after Pierre Curie rather than Marie Curie. The Ising model was introduced actually by Lenz. So Ising was a student of Lenz, and I think the only thing he did was to sow confusion. Lenz gave him this project, work on the Ising model, like trying to understand if it has a phase transition. He didn't call it the Ising model, obviously. Go work on this model, right? And what Ising did in his thesis was he showed that there's no phase transition in one dimension, which of course, I think, from our perspective as probabilists now, this is obviously a very trivial thing, but of course they didn't have necessarily the right way of thinking about things back then. And somehow people were like, oh, okay, I guess the Ising model doesn't have a phase transition, and it took like 20 years or so until this work of Peierls, who sort of resurrected interest in these things, partly because he found there were other physical systems, other models that were well studied for like alloys and stuff like that, that were equivalent to the sync model. So it gave it more physical motivation for working on. But he also showed that there actually is a phase transition once you get to 2 dimensions and higher. Okay, and so this is the argument that I'll show now. Again, it's actually much easier in the case of percolation, but in fact, the 2 theorems are equivalent to each other. So a graph has a phase transition for the sync model if and only if it has one for percolation. That's not very hard to prove, actually. Anyway, let's do it for percolation. Okay, now the first thing to notice is that it suffices to prove that the square grid has PC less than 1. Why is that? Well, the square grid is a subgraph of all the higher dimensional grids, right? So, if you have an infinite cluster inside the subgraph, then of course you have one in the whole graph, okay? You can actually do this argument directly in ZD, but it's significantly more difficult to do. Well, that might be overstating a bit, but anyway, we can certainly restrict attention to 2 dimensions. Okay, now here's the idea. Suppose, by the way, I'll always write K to mean the cluster of the origin. If I want to take the cluster of a different point other than the origin, I'll use a subscript. Is finite. Okay, so maybe it looks something like this. It could have some holes. Okay, now what we notice is that I get this kind of outer boundary of the cluster, right? So if I look at any of the edges which are adjacent to but not included in the cluster, then they must be closed, right? Because otherwise they'd be in the cluster. And so what you'll see is they look something like this, maybe. Okay, and in fact, what happens is, if you study percolation in the plane, there's a very useful thing you can use, which is planar duality. So in general, if you, right, so maybe I'll just draw a quick picture. Right, so let's say this is the square grid, right? What is the planar dual of the square grid? Well, it's just a different square grid, right, that's offset slightly. Right, so the planar dual has, its vertices are the faces of the original graph, its faces are the vertices of the original graph. The square grid is its own planar dual, just with this offset, right? And what we can do is we can define a configuration by saying, every time I see an open edge let's say this edge is open, right? That means I do not include the dual edge that crosses it. But conversely, if I see a closed edge, so maybe this edge is not there, then I do include the dual edge that crosses it, right? So in other words, the dual edges and the primal edges are in bijection with each other, and I define the dual configuration by taking the complement of the original configuration and then mapping through this bijection, right? So they're all the edges that are not crossed. Okay, now what happens when you have this picture is you actually get a circuit in the planar dual surrounding this cluster. Okay, this is a topological fact of the kind that I would really prefer not to have to prove to you, but hopefully you find it relatively convincing. I mean, it's a discrete version of Jordan-Curve theorem, maybe. Yeah, anyway. The point is, if you have a finite set, you can define its outer boundary. It's a path in the dual that surrounds the set. Okay? Now, and the point is all of these edges must be closed in the primal, open in the dual. Okay? So what we can do is we can bound the probability that the origin is not connected to infinity, right? Meaning it's in a finite cluster, by the expected number of closed circuits surrounding the origin. Okay, and now we can just use a very similar argument to how we prove PC is positive, right? So what's the idea? The thing that's slightly more complicated than before is that, before we were counting paths starting at the origin, and now we don't know where they start. Okay? So let's do it similarly to before. So we'll sum over n. And for each n, we'll look at all the parts that could be this closed circuit surrounding the origin of length n. Of course, the probability that one of them is closed is fully closed is 1 minus ptn. And then I need the number of simple paths of length n surrounding the origin. Okay. And remember, we're not trying to compute PC here, right? In fact, I think it's not really reasonable to compute PC via this kind of method. So let's satisfy ourselves with a pretty rough bound. Okay. So, okay, here's the first point. Okay, now let's look at where our path crosses the positive real line, right? Like the positive x-axis, right? Well, it has length n and it surrounds the origin, so it has to intersect this positive x-axis somewhere in the first n places, right? Just have time to get back. In fact, it's like n over 2, I guess, but let's not worry about optimizing. Okay, so we'll get a factor of n for choosing where we cross one place where maybe the first place where we cross the real line. Of course, it could cross many times. Okay, and then we just say, well, similarly to before, once I've chosen that, I just have at most 3 choices for how to continue the path, right? I can go straight, I can turn left, I can turn right. Okay, so we get this bound on the number of paths. Again, this is of course not optimal. There are fewer than this by some exponential factor, but let's that's not what we're trying to do. Okay, so what I get is, in putting this together, I get this sum. Okay, and what you can see is that if p is close enough to 1, then this converges. And in fact, if p is really close to 1, then it's arbitrarily small. So p is close enough to 1. Okay. In fact, you just need it to be finite, and that's a nice exercise. Prove that if this sum is finite, then in fact you have you have an infinite cluster with positive probability. But let's just do more than we need to and make it less than 1. Okay. Any questions on that? Okay. So once you have this theorem that you have a phase transition in more than 2 dimensions, the theory then kind of splits 3 ways roughly, right? So you can choose, am I going to study P less than PC? Am I going to study P more than PC? Am I going to study P equal to PC, right? And these are all like valid pursuits. For this course, we're going to be focusing, as I said, more or less entirely on the P equals PC, or at least P very close to PC, which is not to say that there aren't interesting things to prove about the other regimes. In particular, the critical theory ends up being quite tied up with the subcritical theory, so we will talk about that. We won't talk very much at all about the supercritical theory, but there's a lot that you can say there. So, typically, if you were going to develop that topic more, what you'd want to say is that when P is larger than PC, you have a unique infinite cluster, and its geometry is very close to that of the lattice that you started with, basically. The random walk on the cluster will converge to Brownian motion and all this kind of stuff. There's a lot of things you can do in that direction, but I'm not going to be talking about them in this course. Okay. So what we want to do is focus on critical percolation. And the main thing I want to talk about the rest of today is basically what like the big picture is in terms of what's conjectured to be true. And I'll say a little bit about what's known. And then over the course of the rest of the week, I'll show you the proofs of some of the classical known things about critical percolation, and then I'll tell you about the new things I've been doing, which are basically towards understanding these conjectures for a slightly different model, which is long-range percolation. So PC, right, it's defined to be the boundary between the phase where you do not have infinite clusters and the phase where you do have infinite clusters, right? So the first basic question you can ask is, are there infinite clusters? PC. Okay. Now, and I'm thinking primarily on ZD for the purposes of this course. Okay. Now, okay, there's one case I can tell you very easily. Of course, in one dimension, PC is one. So, of course, PC is one, then you certainly have infinite clusters of PC, if the graph is infinite, anyway. And the conjecture is that no for D at least two. Okay. And this is known for D equals 2, where it's, well, maybe I should say it's the theorem of Harris and Keston, completed by Keston in 1980. And it's also known for D much larger than 6. Now, of course, being much larger than 6 is the same as being much larger than 1, but we'll see why I've phrased it this way soon. And this is from around 1990. So, we should have been doing a new theorem in 2000. Didn't happen. So this is not like the end of the story, of course, with these things. So I should say, why 2 dimensions and high dimensions? Well, 2 dimensions is very special for a variety of reasons. So, as we just saw in our implementation of the piles argument, planar duality is a very special tool that you have available only in 2 dimensions. You also have just the very restricted topology of the plane, right? Things about like, if you have a box and you have a path from the top to bottom, left to right, they have to cross each other, things like this that are just very special to 2 dimensions. And, I guess these are the main things ultimately powering this proof. There are other special things about 2 dimensions too, but I'll get onto those in a bit. Okay. Now, what about high dimensions? Well, as I'll say in a lot more detail soon, it turns out high dimensions is just easier in some ways than low dimensions. But I'll talk a lot more about this in a bit, so let me just leave that mysterious for now. Okay, so I should say, the reason why you need the dimension very large is sort of an artifact of the proof, but the record for ZD is D at least 11. This is due to Pfitzner and van der Hofstad. Although, really, morally, these techniques should be pushable down to D just strictly larger than 6. And in fact, if you're willing to change the D-dimensional lattice that you work on, then they do work down to D equals D strictly larger than 6. Okay. So, this course, though, this is not really about this qualitative question. It's about the question we would like to answer after answering this question, or maybe in parallel, because actually often these things go together, which is to understand not just that there are no infinite clusters at PC, but we want to understand what do the finite clusters that do exist actually look like, right? So what we expect is that, in fact, we know that below criticality, when you're really subcritical, the probability of the origin being in a large cluster is exponentially small. Being in a cluster of size n is exponentially small in n, below PC. Whereas at PC, it should have some kind of power law. So it should be, although you don't have infinite clusters, it will be relatively easy to have large finite clusters. And in particular, if you look at like a big box, you should see clusters which are like macroscopic, like their diameter is of the same order as the box, things like that. So what we'd really like to do is not just know that there are no infinite clusters, but to say, can we develop a theory of what the finite clusters look like? Okay, and there are kind of two main approaches, which are again things that you really in practice are done in parallel, which are critical exponents and scaling limits. Okay. So basically what I mean by this is, when you're studying things from the perspective of critical exponents, the idea is that various interesting quantities should have power laws. So let me give some examples of this. So for example, I mentioned before that K will be my notation for the cluster at the origin. So if I write this, it just means the number of vertices in the cluster at the origin. So one thing you expect is that if you're at criticality and you look at the probability the cluster at the origin has at least n vertices, it should decay like some power event. Okay. Now, one thing with these critical exponents is that there's a sort of system of traditional names for them that was introduced by Fisher. And when you first see these, it might seem a bit stupid, like the way you write them and so on, but it's actually all been worked out for your benefit. So it is actually good to use this system of traditional names for the exponent, partly because then if well, one thing, if you talk to your colleague, you can say, oh yeah, well, I proved that delta is 2 or whatever, and they'll know what you mean. Another thing is that Fisher worked them out so that the same exponents appear across a range of different models, and they're sort of the correct analogies are drawn by using the system of notations that he introduced. So for this one, for the volume tail, the traditional name is 1 over delta. Okay? Now, I'm going to reserve this wiggly equal sign just to mean some kind of heuristic thing where I'm not giving you a precise definition of what it means. In particular, this should mean this. Okay. But when doing heuristic arguments, you don't necessarily want to figure out exactly the sense in which the asymptotic equality holds, given that you're just doing a heuristic anyway. So it would be useful to have a non-specific heuristic equality sign. Okay. Okay, so this is one. This is delta, the volume tail exponent. Another one is the 2-point function. So by the 2-point function, I just mean this probability that x is connected to y by an open path. Okay, and this should also have some power law decay. And in this case, the traditional notation is minus d plus 2 minus eta. Okay. The reason roughly that you write it this way is that we'll see in high dimensions, you have Green's function scaling of the 2-point function, which means minus d plus 2 scaling. So eta is like the correction to Green's function scaling. Okay, so that's another one. Of course, one can go on like all day defining more and more exponents. So let me just tell you a couple more. So one is we look at the expected size of the cluster at the origin. Of course, this is the same as summing the 2-point function, right? And this, so one of the most important basic theorems in percolation is called the sharpness of the phase transition. So this quantity is called the susceptibility. just the expected size of the cluster at the origin. In general, if you're working with a different statistical mechanics model, the susceptibility usually means the sum of the two-point function, whatever that two-point function is. Okay, and the sharpness of the phase transition tells you that this is finite if and only if P is less than PC. So let me just I probably won't have time to prove this week just because there are other things that I would rather do. But in any case, this theorem is called the sharpness of the phase transition. It has a long history. It was open for a long time in the early history of percolation. I think, it was something that was clearly recognized, like so percolation was first studied by Broadbent and Hammersley in the mid-50s. This was very quickly realized that this would be a very desirable theorem to have. And I think it was proven in like the early to mid 80s. So, it was open for sort of 30 years or something. And, if you look at very old papers on percolation from before then, they actually have two different critical points, which are called PT and PH for, I think, Temperley and Hammersley. I can't remember which one is which, but one of them is the one we defined, and what the other is where this becomes infinite. Of course, we don't need that distinction anymore. Yeah. Yeah, let's always be on ZD now. But this theorem is fairly transitive graph, actually. But of course, it's not true without transitivity. Yeah, sorry. Okay. So in fact, this was eventually proven in independent works by Menshikov and Eisenman and Barsky, but both in the early 80s. And now there are like 5 or 6 different proofs. It's sort of become I don't know, there's certain kind of mathematician who really likes finding new proofs, the prime number theorem. This is like how, not the prime number theorem, sorry, the infinitude of the primes, Euclid's theorem. And that's maybe become our version of this for some small corner of probability. But anyway, one interesting thing is that all these proofs actually tell you something a bit different in addition to this. And it's an interesting story, but I think I may come back to this later in the week, but we'll see how we do. Okay. So anyway, this is finite for P less than PC, and it has to blow up as you approach PC. So it should blow up roughly like some power of epsilon being how close you are to PC, and the traditional name for this is gamma. Okay. So you might be wondering at this point, why should everything have a power law? I think there's a tendency, like I think when I have heard this as a student, people would often say, "Oh, physicists tell us that that's the case." Well, it's for some physics reason. I think that's a really bad, that's a really bad reason. So essentially, like the reason why one should have power laws is because you should have scale invariance. So of course, that's maybe just pushing it back another layer, like, okay, well, why do you have scale invariance? But basically, if you think about the function which just maps x to a power, that function has this nice scale invariance property, right? That if you, like f of lambda x is equal to some, of course you could compute exactly what this is, but right, powers have this scale invariance property, right? And in fact, they're the only functions that have this scale invariance property. So ultimately, the fact that we get power laws is just a reflection of the fact that we have some kind of scale invariance asymptotically in this system of criticality. Okay, then you could say, well, why do you have scale invariance? Well, okay, then maybe we get a little bit closer to just saying, well, physics tells us so. But in fact, there's a good reason for that too, which is roughly that Um, when you're away from criticality, you know, there should be some distinction between like what the system looks like at small scales, and then eventually when you zoom out far enough, you'll just see, oh, I'm not at criticality. I just see like something not interesting, right? Like when you're subcritical, eventually you zoom out and you just see tiny clusters that are failing to connect in any interesting way. When you're above criticality, you zoom out, and you see this more like homogenization type regime where like eventually, oh, it basically looks like ZT. Like it's just I've just recovered Euclidean geometry, right? So, you know, away from criticality, there'll be some scale at which which is called the correlation length, and you should think of it as something that is vaguely defined. There are many precise definitions one could make that are not obviously equivalent to each other. The scale at which you start transitioning between looking off critical and looking critical, right? And this is kind of a characteristic scale of the model, you know. And at criticality, there should not be any characteristic scale. That's almost like what it means for a model to be critical. Of course, you know, proving this is the case is another matter, right? But basically, if you don't have scale invariance, it kind of means nothing interesting is happening at criticality. You know, well, not, of course, you could have some oscillation or something. You know, as mathematicians, we have to deal with all kinds of pathologies like this. But roughly speaking, the fact that you should see interesting things at all scales, barring some pathologies, means that you have some limiting scale invariance. If you have scale invariance, you have to have power laws because they're the only scale invariant functions of a single variable. Okay. So, okay. So one of my goals with this course is to hopefully demystify some of these things where often when you see a course, they'll be like, oh, well, physics says, you know. I actually think often these things have nothing to do with physics as far as I can tell. They just have to do with, you know, a bit of willingness to engage in heuristic reasoning, right? I didn't tell you anything about like moments of inertia or something, anything like that, right? Okay. Good. So that's like the picture with critical exponents. So I'll talk more about those in a second. Um, you know, the other thing we expect to have are scaling limits. So I'll be a bit vague about this for now. Basically, you know, if we take our system at criticality and then we zoom out, we expect to be able to take a limit, right, where you're rescaling. You know, you can think about working in RD and sending the spacing of the lattice to zero, right, instead of zooming out with a fixed lattice. And ideally, at criticality, we should see some kind of interesting scaling limit, right? As I was just saying, you know, you should also get scaling limits away from criticality, but they should be like non-interesting scaling limits. Okay, so exactly what like things with taking limits of that really depends on the different exact setting, right? But you could think, you know, you look at the cluster at the origin, maybe you condition it to be large or something. You think of that as a random metric space. You try and scale it. Can you say something interesting about what happens? Um, so, you know, somehow the idea is to try to take a limit of the entire system rather than just like one particular quantity, which is kind of what you're doing when you look at critical exponents. So you can imagine that usually results about scaling limits are stronger than results about critical exponents. So, okay, these some definitions, so not even like what can we actually prove about them? Well, um, let's start by talking about high dimensions. Um, and yeah, the story I'm about to tell is not very specific to percolation. And in fact, I find it more convincing to give an explanation for self-avoiding walk first, and then we'll go back and talk about percolation. Let's just check time. By the way, there was some discussion whether we should have like a 5-minute break at some point. Where it's 11 o'clock now, I just saw. So anyway, I don't know. Maybe let me talk a bit more first. Okay. So the basic idea that happens across many different models of statistical mechanics is that you have what's called an upper critical dimension. above which the behavior of the model becomes what is often called trivial. Okay, now, these are actually pretty interesting things, and one shouldn't take the word trivial too seriously. But essentially what that means is you can often think about your model as being some kind of simple model that you then add some kind of interaction, some interesting feature to, right? So let me explain this in the context of self-avoiding work. Okay, so what is self-avoiding work? You take a uniform, random, simple path of length m. Okay, equivalently, this is on ZD, so let's say. Equivalently, condition simple random walk to be simple, right? So self-avoiding just means simple. It means you don't visit the same vertex more than once. Okay. And what kind of questions can you ask about this? Well, the same ones we were just asking about percolation, right? So, you can study some interesting quantities of, for example, you can say, how far away is the endpoint typically, right? Presumably that grows roughly like some power of n, right? Or you could try and take the scaling limit, okay? And the idea is that, this self-avoiding walk is simple random walk plus an interaction. Okay, where the interaction just means okay, in this case it's like it's a hard interaction. We're just saying some configurations are forbidden. You can also do what's called weakly self-avoiding walk, where you just introduce like you make walks that intersect themselves less likely. But let's stick with this one. So, and the idea is that in high enough dimensions, so above what's called the upper critical dimension, DC, which depends on the model. So for D bigger than DC, the interaction is irrelevant. Okay. So, here I'm just talking for now about like the heuristic theory. So what should that mean? Well, it should mean that basically it's behaving in some sense roughly the same as the model without the interaction once you go to high enough dimensions. Okay, so what should this mean for self-avoiding walk? It should mean that in high enough dimension, self-avoiding walk should behave basically like simple random walk. Okay, now, one thing I want to stress here is that this event that you're conditioning on, the event that the simple random walk doesn't intersect itself, this always has very small probability. It's not like a transition from this event having very small probability to like reasonably large probability. It's nothing like that, right? Like no matter what dimension you're in, this is always an exponentially unlikely event, right? Because every time you take 4 steps, you have some constant probability of closing a square and making itself in section. But, somehow the nature of the event changes in some way. And it turns out for self-weighting walk, the critical dimension is 4. And there's an easy way of at least understanding why this might plausibly be the case. Okay? Like what is the change in behavior of the simple random walk that's happening in 4 dimensions? Which is that if D is larger than 4, 2 simple random walks intersect finitely often, almost surely. Okay, so in particular, if I run one long simple random walk and I look at a point somewhere in the middle, of course it could have some, self-intersections or whatever, but they're going to be like localized, right? Because, if I took a limit, of course, like looking at a simple random walk from a point in the middle and then taking a limit, I just get 2 independent simple random walks going off to infinity. And this is saying, above 4 dimensions, those self-intersections, they occur on, there's only finitely many of them, they occur on scales of order 1, right? So the interaction is kind of localizing. Even though, as I said, the probability is always exponentially small, it's at least plausible that once you have this picture where, these intersections are localizing, in particular, if you take the scaling limit of the simple random walk, right, you get Brownian motion. And in Brownian motion in dimensions 5 and higher, it does not have any self-intersections. It's almost surely a simple curve. Okay? So in dimensions above 4, this interaction is kind of localizing. So even though it's a very unlikely event that you're conditioning on, it's like a local kind of event. So in particular, it's actually a theorem, which I guess is due to Hara and Slade. Which is that for D at least 4, the self-avoiding walk converges to Brownian motion. Okay, the same as simple random walk. Now, the difference with simple random walk, so we are still conditioning on an unlikely event. And the way that's manifesting itself is just that, if you take your self-avoiding walk, N, right, hopefully I got the powers right there. So, this is how you would take the limit of simple random walk to get Brownian motion, right? If you do this with simple random walk, you get Brownian motion with a particular variance. And, if you do this with self-avoiding walk, you really get a different limiting variance for your Brownian motion. So, there is still an effect at large scales of the fact that you introduce this interaction, but all it's doing is changing like the limiting variance of the Brownian motion. Of course, that does mean that limiting Brownian motion, it's mutually singular with respect to the standard one, right? In some sense, it's quite different, but not in most senses that we care about. Okay, so in particular, what happens here is, you get the same scaling limit with the same scaling function, right? So you have to, in particular, what they show is that in high-dimensional self-leading walk, the displacement is still governed by this like central limit theorem type scaling that you get for simple random walk, right? You run a self-leading walk for n steps, it's probably going to be a distance about root. Okay. Now in dimension, oh, and I should mention the fact that you get it all the way down to the critical dimension here, actually the method is the same as for percolation, but it just happens that numerically they were able to optimize it enough that it goes all the way down to 5 dimensions. Okay, in dimension less than 4, if you take this simple random walk, the self-intersections are much more severe, right? So if you have, you've all seen pictures of 2-dimensional Brownian motion, they were more beautiful than that. But it intersects itself a lot, right? And like on the same scale, right? So if you have a Brownian motion, you run it for a random walk in low dimensions, you run it for n steps, it will have intersections that are on the same scale as its diameter. In low dimensions than in high dimensions. Okay. Of course, there's very little actually proven about low-dimensional self-avoiding walk. Yeah, almost nothing at all, actually, I would say. We do actually have a conjecture for what the scaling limit of the 2-dimensional self-avoiding walk is, which is one of Schramm's SLE curves. It's 8/3, right? Yeah. So it should be SLE 8/3, but that's an open problem. We do know that if it has a scaling limit which is conformally invariant, then it has to be SLE 8/3. Anyway, I think this picture of what's going on, where you start with the simple model, which physicists would often call a Gaussian model, right? In this case, just simple random walk. You add some kind of self-interaction to it that makes it interesting. In high enough dimensions, this interaction should no longer have a significant effect at large scales, although it does do something, namely like change the limiting variance of the Brownian motion. Okay. maybe that's a good time to take a muffin break. And I'll tell you how this works for percolation afterwards. Maybe we can start again in 5 minutes. So, yeah. What? I mean, it's proven that the self-Wheeling walk is it does not have linear displacement, right? I think Christophorus improved this to n over log n or something, right? But the hexagonal lattice through it.
No.
Uh-huh.
Great stuff.
Thanks.
You work here.
And then can I take well, I don't. Well,
yeah, it's true. And you have one lecture on high school.
one intro line is the best everything.
Yeah, the double lecture, that's like.
Correct. That's right. Yeah, I love that. So, but yeah.
No, so it's not.
2 weeks. 2 weeks.
The next week is fresh week. Party.
Right.
Sorry, because it's it's just last chance.
Sorry?
Last chance to take seven.
Right, yeah, exactly. I know. We had a group of the yeah, but that's why we did. Yeah. Yeah, I don't know. I'm texting perfectly right. Because my first job was this was where I was. The first time in my this time public. Right, so I mean,
It would have been 3 weeks.
it's 3 weeks. Yes. I mean, I guess it's not.
So they could have. That's not really near. They need to together seven. Right. Hopefully there isn't that.
So you send your kids to school or to get private?
So you say Sorry. So it's a video bullshit. Right.
I've told this at
So what
Yes,
you told me?
it's, one of
I told you it's not a good news, but then you look at all the.
So I bet was only because they required it. Yeah. Now it's every day. Now it's today and Thursday.
And I now know.
No, it doesn't matter.
This is people.
I think so that's then we just
So it's
the sum of so just right. So the idea is that
Now I'm ready. When I was on the I was totally confused what yeah, that's just
last year.
so it's
Yeah, you can put them Normalement, on aurait des soirées et là, il y a eu dans 3 ans.
No, she doesn't.
Thanks always for it.
Ça, c'est sûr. Quand ma mère, elle m'a fait.
Should we get started again?
C'est que
And then you take the net and
Okay. Right. So I was just telling you this basic picture of the transition between low and high dimensional behavior for self-leading work. And maybe a couple of other points of terminology. So this high dimensional behavior you get above the upper critical dimension. This is usually is often called mean field critical behavior. The reason for the name comes from analogies with the Ising model again. And if you do the Ising model on the complete graph, which is also called the Curie-Weiss model, it's like every spin, it's a random field, and every every spin in the field is interacting with the mean of the field, right? That's why it's called mean field. Of course, that doesn't really make sense for self-leading walk, but that's just the name. Okay. And, you know, I stated it here in terms of the scaling limit being Brownian motion, but also in high-dimensional self-leading walk, you'll also get all the same critical exponents as the simple random walk as well. And I'll talk about that more in the context of percolation. Okay, so the reason I like to do this brief divergent self-leading walk is, of course, for percolation, it's much less clear what is the non-interacting model that you're adding an interaction to get percolation. Right? It's like in self-leading walk, it was almost defined that way. And of course, this is not like a precise mathematical thing, right? But let me give you a story of how you might think of percolation as something easy plus interaction. So the idea is that percolation is like branching random walk. Plus interaction. Okay, so let me explain what I mean by that. So what is branching random walk? It's a Markov chain where at each step you have finitely many particles, right? And at each step, these particles all split into some number of children. So you never think about one particle surviving. It could have one child, but you know, let's keep the generations disjoint. Okay, and these children also move. Okay, and you can do this where either you know the branching and the movement are independent or they're not. So you know one particular way you could define branching random walk that makes the analogy with percolation most clear is you would say that that each particle has a child, has at most one child at each of its neighbors independently with probability P. Right, so you know, at each stage you have some cloud of particles, each one of them is at a vertex of ZD, each one looks at each of its neighbors in ZD and independently chooses to have a child there or not with some probability P. Okay, this defines a version of branching random walk. And so what's the relation of this with percolation? Well, you could imagine if you're going to simulate percolation on your computer, here's a simple way you might do it, right? You say, I'm going to just explore the cluster at the origin with a breadth first search, right? So I start off with the origin, I look at all the edges incident to the origin, and I decide, are they open or closed in the configuration, right? So I flip a coin for each one. And then at step 2, you have these vertices that you discovered that you found were neighboring the origin in its cluster, and you have to continue the exploration, right? So you need to look at all the edges coming out of those and say, are they open or closed, and etc. Now, of course, the important thing you have to remember, and which you might fail to remember if you're coding this badly, is that you know you're not allowed to reuse an edge, right? So you know edges, once they've revealed to be open or closed, they're open or closed forever, and moreover, you're not going to reuse an open edge that you already used. Okay, so this distinction is exactly what differentiates percolation from this model of branching random walk, right? If you were a lousy coder or you know asked your favorite LLM to write the code for you and you didn't check it properly, you might end up generating branching random walk instead of percolation by ignoring this no backtracking rule that percolation has, right? So hopefully that makes it clear that you know percolation is kind of similar to branching random walk, but you've added this constraint that it's not allowed to reuse things that it already used. Okay, and so the idea is that in high enough dimension, this interaction should be irrelevant at large scales, meaning that you should get the same scaling limit for percolation and for branching random walk. Now, one important thing to stress there is that this absolutely does not mean that the critical probabilities will be the same, right? So, you know, if you actually think about this, what I just described, this way of sampling percolation and sampling branching random walk, it actually gives you a coupling of the two models, right? It lets you define them both on the same probability space so that branching random walk always has like more particles in, right? Because some of the offspring are like forbidden and you delete them in the percolation, not in the branching random walk. So you might think, oh, well, you know, percolation is easy, you know, I want to prove there's no infinite clusters at PC. Well, I'll just use the stochastic domination with branching random walk, right? It's pretty easy to prove there's no infinite clusters at criticality for branching random walk. But of course, that doesn't work because the critical probabilities are different, right? So you do have stochastic domination, but because the critical probabilities change, you can't actually argue that way. But nevertheless, what we do expect is that in high enough dimension, critical percolation looks like critical branching random walk at large scales. Where again, branching random walk is the like Gaussian or like trivial model. It's the reference model that you're adding the interaction to. Okay. Okay, now that's at least should be kind of reasonable, right? Once you get to high enough dimensions, you have so much space. It's like, well, who cares that when I occasionally come back and intersect myself, I have to delete that vertex. You know, it's at least plausible that that's not really changing anything in high enough dimensions, right? If you're doing percolation on a tree, by the way, it's, you know, of course, if you define the branching random walk correctly, you can make them exactly the same. Okay. Now, what might be less clear at this point is like, what is a high enough dimension? Right, in the case of self-voiding walk, we had this reasonably nice story about why it should plausibly be 4. Oh, by the way, I should have mentioned this, the fact that simple random walk intersects itself infinitely often, if and only if D is at most 4. That's a theorem of Erdős and Taylor from the 1960s. It's also quite easy to prove, so you should go away and think about that for yourself if you haven't seen it before. The most subtle case, by the way, is dimension equal to 4. In that case, what happens is that the two random walks do intersect infinitely often, but the number of intersections only grows logarithmically. And as I'll talk about in more detail later, what that eventually should lead to, although we actually can't prove that yet for self-voiding walk, although there are some similar results for slightly different models, is that you should still get convergence to Brownian motion, but you have to add in appropriate powers of log to make the limits come out correctly. And we'll see. I'll talk about that in the analogous things in more detail for percolation. Okay. Okay. So what should be the critical dimension here? And it turns out, and for now I won't explain this, but we'll come back to it. It turns out that for percolation, the critical dimension is 6. I'll give you a few different ways of understanding this over the course of these lectures. Okay. So what can we actually prove? Yeah, it would be helpful to leave these on, actually. So I mentioned earlier, in regards to the problem of whether there exist infinite clusters at PC or not, that this problem was solved in high dimensions by Haar and Slade. And in fact, it wasn't really that they just proved that. They really proved, they developed a very comprehensive theory of the critical behavior at PC in high dimensions. This is using a technique called the lace expansion, which is kind of a systematic way for many different models to prove that you have mean field behavior in high enough dimension. So it was introduced, I won't really talk much about the lace expansion, but it was introduced in the 80s by Bridges and Spencer as a way of proving that this weakly self-voiding walk model, which is like, again, self-voiding walk, but you just make parts with more intersections less likely rather than forbidding them, proving that that has mean field behavior in high enough dimensions. And then Hara and Slade really like took this idea and ran with it extensively, and they applied it to many other things. They improved it a lot. So in particular, they were able to analyze percolation. And what they showed is that if D is large, or, and you know, this is why I wrote D much bigger than 6, right? Because you actually should only have this behavior down to 6 dimensions, or D strictly larger than 6, and spread out lattice. So what this means basically is that instead of working on ZD, you work with this graph ZDL, where X is adjacent to Y if and only if they're within distance L of most L of each other, and then you take L very large. So, you know, this method, the lace expansion, it requires some numerical assumptions beyond the minimal assumptions you should need to actually get the high dimensional critical behavior. But it can either be very high dimensions or very spread out lattice. Then you get, for example, that the probability the cluster at the origin has size at least n is like 1/√10. This means up to constants, by the way. So it means, you know, the left-hand side is bounded by a large constant multiple of the right-hand side and bounded below by a small positive constant multiple at the right-hand side. The susceptibility, so the expected size of the cluster at the origin blows up like 1/epsilon, and you know, many other things too. Okay, so these are all the mean field values of these exponents. And in fact, what you should think for these ones is actually when you do branching random walk, well, depending on exactly how you define branching random walk, I define this one that's closer to percolation. It actually doesn't have this nice property. But if you do the one where the branching and the splitting are independent, then what you can think that when you do branching random walk that way, you can describe it equivalently by first sampling the genealogical tree of the particles, which is just like a branching process, a Galton-Watson tree. And then you embed that into space using random walk. So in other words, that you take a uniform random homomorphism of that tree into ZD. Okay, and if you do that, then these things about like the size of the cluster, well, they don't depend on the embedding, right? So actually, you should think these are just, you know, for branching random walk, these are actually just branching process quantities, right? And you know, this is saying that in high dimensions, this percolation cluster is behaving like a finite variance branching process, right? So this 1/√10 is the same tail probability as saying if you have a finite variance branching process at criticality, what's the probability has total progeny at least n, which case like 1/√10. And similarly, for a branching process, this is actually, I think, even an inequality, right? Because you have this thing where the expected number of particles at generation n is exactly the expected offspring at time 1 to the power n, right? It's exactly a geometric series. So you're just summing a geometric series and you get 1/epsilon. Okay. Now, one thing they didn't quite do in this paper was to get the behavior of the 2-point function, namely the probability x is connected to y. In fact, what they did is they got sharp asymptotics of the Fourier transform of the 2-point function, which for many purposes is just as good. But this was improved by Hara, van der Hofstad, and Slade. So in other words, just adding in Remco to the mix. They showed that also under the same assumptions, the 2-point function is up to constants this distance to minus d plus 2. Okay, now this power, again, you should think that this is like the Green's function. Okay. So you know, the Green's function, the way it's normally defined, it's you run a random walk from X and you say what's the expected number of times it visits Y, or sometimes just the probability it hits Y. These are just constant multiples different from each other. And this is actually the same as running a critical branching random walk from X and saying how many particles visit Y. Just it's a linearity of expectation thing. In a critical branching process, in expectation, there are 1 particles in each generation, so you get the same quantity for the simple random walk and critical branching random walk Green's functions. Okay, and you know the fact that the Green's function behaves like this, of course, is something very classical. Okay, so again, you should think that this scaling of the connection probability means that it's another instance of high-dimensional percolation behaving like a branching random walk at criticality. Okay. And you know, as I said, there are many other exponents that are understood, but I won't go through all of them now. Maybe let me say one thing, which is really what they proved is that, and this is something I'll explain in more detail tomorrow, maybe, is that high-dimensional percolation satisfies something called the triangle condition, and this was already known through works of other people like Eisenman and Barsky and Eisenman and Newman to imply these values of the critical exponents for at least for the first 2. So and I'll actually go through that proof of, well, I'll tell you what the triangle condition is, and I'll show you that it implies these at least this one for the susceptibility, the critical exponent. Good. So there are many other exponents one can look at. One thing that was not done yet, but which hopefully will be on the archive quite soon, is also the scaling limit. So in fact, there were some related results by another group also looking at different aspects of the scaling limit recently. But I won't talk much more about this. But with Arthur Blanc-Renaudy, we have a forthcoming paper showing that under the same assumptions, so you know, basically assuming you can implement this method, then the scaling limit is the same as branching random. And this is what's called super Brownian motion. Okay, I'm not really going to go into any detail about what super Brownian motion is, but you know, it's the scaling limit of branching random walk. So it's a measure valued diffusion. You have, you know, you should think that you have like infinitesimal particles which are diffusing and like continuously branching all the time. Yeah. Anyway, so we now understand this high dimensional case pretty well. Okay. Now, what about low dimensions? Of course, though, you know, it remains a really important problem, I think, to find a different way of doing this, which does not have these numerical assumptions, right? I mean, it would be very nice to just say, okay, if D is bigger than 6, you're good. You know, everything else is proven. And I should say, you know, many of the steps of this are like more in that, you know, they say if some estimate holds and another estimate holds, those are fine. But to get started and basically prove like any one of these estimates under the minimal assumption that D is just larger than 6, no additional numerical assumptions, I think that's a very interesting problem. Good. Okay, so what about low dimensions? So the idea is that, you know, once you get below the critical dimension, the model really starts to like feel this self-interaction that it has with itself in a serious way that actually change the exponents, and they change the scaling limits and all of that stuff. Okay, at least, you know, conjecturally that's what happens. Okay, now there's really just one case where we understand this well, which is in 2 dimensions. And in fact, and you should think, you know, by the time you get down to 2 dimensions, this way of thinking about percolation as branching random walk processing track, I mean, this is going to be basically completely useless for most things. I mean, percolation is really not behaving anything like branching random walk anymore. So it becomes a less useful way of thinking about things. And there's really just one case that we understand well, which is site percolation on the triangular lattice. Okay. We have many conditional results about other lattices. So this is the only case where we know that the model has a conformally invariant scaling limit. So that was proven by Smirnov. And I think we know that all the things about exponents and what the scaling limit actually is, you know, it's known that if you have a conformally invariant scaling limit, then they must be these things, but this is the only case where we can prove that. And in this case, oh, sorry, I should have explained what these things mean in terms of the exponents. So just going back to high dimensions briefly, this exponent here means delta is 2. This one means gamma is 1. This one means eta is 0. Okay, so you can see in particular that these exponents have very simple values in high dimensions. Okay, what about 2 dimensions? So there's a very funny thing that happens in 2 dimensions, and again, this is not very particular to percolation, which is that the exponents take like strange but rational values that you can compute. Okay, so delta is 91/5. Eta is 5/24. And gamma is 43/18. Yeah, you can see, you know, I've given this course a large number of times. I don't really need notes anymore. My only notes are this and one other, some other rational numbers I'm going to tell you in a minute. Okay, you know, this is how you can tell I'm not really a 2D percolation guy because I haven't memorized these. Okay, so I should say, you know, these were conjectured or predicted, perhaps is the better word, by a physicist, Nienhuis, some decade or two before they were proven. And, you know, this is a culmination of a work of many people. So as I may talk about later in the week, there are believed to be, in quite high levels of generality, relations between the various exponents. There are what are called scaling relations, which hold in all dimensions, and hyperscaling relations that only hold in low dimensions. And these were proven for 2-dimensional percolation models by Keston. You know, assuming that the exponents are well-defined, or at least some of them are well-defined, then the rest are, and they satisfy these relations. And then, you know, Schramm introduced the theory of SLE, which gives you the description of what the scaling limits are. And for percolation, it's SLE 6. And then once you have the SLE picture, you can start computing exponents, and this was done by Lawler, Schramm, and Werner. So. Okay. Of course, you know, there are many special things going on in 2 dimensions. So as I was saying before, you have duality, you have the topology of plane curves, but you also have complex analysis, right? So, you know, I said this word conformally invariant a lot without saying what I mean. And, you know, I was saying before that you expect critical models to be scale invariant, meaning, you know, if you're at one very large scale or like 3 times that, you shouldn't really be able to tell the difference, right? What does it mean to be conformally invariant? Well, it means that you also can't tell the difference between a very fine mesh lattice and another one you get by applying like a conformal map to it, like a Mobius transformation, for example. Okay? And in 2 dimensions, there are many, many more conformal maps than in general dimension. So, you know, there's the Riemann mapping theorem says if you have any 2 simply connected domains in the plane, which are not the whole plane, then you can map one to the other by a conformal equivalence. Okay, so it means this invariance under conformal maps of the scaling limit is extremely powerful in 2 dimensions. It should still be true, but considerably less powerful in higher dimensions. So, you know, in any dimension, the only maps you have of all of RD, which are conformal maps, are the Mobius transformations. In dimension 3 and higher, those are also the only conformal maps, even when you restrict open sets. So if you have just a conformal map between, I guess, 2 connected open sets, it has to be just the restriction of a Mobius transformation in dimension 3 and higher. So it's actually, you know, in physics recently, not even that recently anymore, really, that, you know, there's been a development of something called the conformal bootstrap, and they found that, that's also a method in 2 dimensions, but it's also been found that this conformal invariance actually still has a significant role to play in the understanding of what's going on in higher dimensional systems too, but that's something I'd say that as mathematicians we haven't really grappled with yet. Anyway, but in any case, conformal invariance, it's probably still important in dimension, you know, 3 or whatever, but it's a very, very powerful thing in 2 dimensions. In particular, it leads to a lot of like very rich algebraic structure. You know, there's like the Virasoro algebra and things like that. And the fact that you're eventually getting these like interesting rational numbers coming out, this is a very 2D thing, and it ultimately relies on there being a lot of connections to other things going on like under the hood. Okay. So I'm not really going to talk very much about 2D in this course, but anyway, we understand at least this one example very well. And, you know, with all of these things, actually, I didn't make this point explicitly, but the critical behavior is always expected to be universal. So it should not matter whether you work on the triangular lattice or the square lattice, or whether you do bond or site percolation or whatever. These are all supposed to have the same critical behavior at large scales. Of course, proving that is like another matter entirely, right? So actually, these high dimensional proofs, they have these numerical assumptions you need to make, but other than that, they really work very universally. They're very insensitive to the choice of lattice, like once you have these nice numerical conditions. Smirnov's proof of conformal invariance for site percolation on the triangular lattice is really a different story. It like relies on some like miraculous things that are happening in that one specific example. Okay. Good. How am I doing for time? Am I going to 12 or 12:15? 12:05. Okay. Good. Okay. Okay. Yeah. Anyway, I don't want to hold people back from their lunch. Okay. I think that's fine. Anyway, I should get to a nice point stop. Okay. So that's 2 dimensions. What about other dimensions? Well, dimensions 3, 4, and 5. Oh, these turn out to be very difficult. You know, or at least there's kind of an absence of good techniques to study them. I'll say a little bit about how physicists have understood these things in a minute, but you know, even for physicists, there's an absence of a good theory. For percolation, there's somewhat more successful understanding for the Ising model, but even there's a lot left to be desired. Okay. Now, before saying about that, let me tell you about 6 dimensions. And I think, you know, this is 6 dimensions is in a very nice place for mathematicians because we actually have very precise conjectures about what happens. And like as of yet, we have proven like nothing. So I think it's an exciting place to be. So in the critical dimension, what one generally expects, as I was saying a little bit about for self-leading walk, is that, you know, at the critical dimension itself, you're just about starting to feel the effect of being in a finite dimensional lattice. You're just feeling the effect of the interaction, but in like a weak way that still washes out as you go to large scales, in the sense that you get the same scaling limits as above the critical dimension. But, you know, I was saying when you do self-leading walk, it's not exactly the same scaling limit as simple random walk, because you get this, you change the constants of diffusivity. So you should think that something very similar is happening at the critical dimension, but that constant amount that you're scaling the diffusivity by, it's no longer a true constant. It's like a logarithm or something, you know, which from the perspective of taking scaling limits has exactly the same effect as a constant, but it's some kind of slowly varying function. Okay, so what we conjecture is first of all that the scaling limit is still super Brownian motion. So the same thing again as the scaling limit of branching random walk, except that one has to put in appropriate log factors to get the scaling limit to come out correctly. And there are precise conjectures about the what the log factors are. I think this is from 78 or I'll just put 70s. Which is that, well, if you look at the cluster, like the volume tail, for example. Okay, so in high dimensions, it would be order 1/10. In the critical dimension, it's conjectured to be larger than this by a factor of log to the 2/7. Okay, actually similarly, if you look at the expected size of the cluster of the origin, in high dimensions, it's like 1/epsilon. In the critical dimension, it's supposed to be like larger by actually the same log to the 2/7 factor. This is, okay, now, what about the 2-point function? So again, in high dimensions, I'll write it with the D. I mean, D is 6, but I feel like it's easier to compare when I write it in. In high dimensions, it would be this. In the critical dimension, it's conjectured to be larger by a factor. Any guesses for this? I know some of you have seen my talk before, actually, so anyway. I'm supposed to trick you into saying 2/7, but it's not, it's actually 1/21. Okay, and you know, as before, there are many other exponents one can discuss, and you can formulate conjectures about what the log corrections are. I mean, in many cases, they'll follow from these. You know, there are other things where you would need to work quite hard to just find the right answer. Okay, good. So you know, as I said, I think this is a really nice case where there are very concrete conjectures. You can go and try and prove them, but you know, so far we haven't been able to. And I'll just say something briefly about why that is. Just check the time. So you know these numbers, they obviously don't come from nowhere, right? I mean, you know, you have to have like some way of analyzing the problem to end up with numbers like log to the 2/7, log to the 1/21. So within physics, the most successful way of studying these kind of problems is via something called the renormalization group. It's not a group, it doesn't have anything to do with the mathematical word group. It's arguably a semi-group, depending on how you think about it. But anyway, it's best to just ignore the fact that it has the word group in, other than that people often use just renormalization by itself to describe a much wider array of different kinds of techniques. Renormalization group is something more specific. And this was a technique that was really maybe not introduced, but brought to maturity by Ken Wilson, who got the Nobel Prize for this back in the 80s. And it's a very systematic way of studying critical behavior. It's also used in quantum field theory. And it's very hard to make rigorous. You know, it involves basically you want to introduce some kind of spatial cutoff to the model. Like often people think about this as like splitting the lattice into big boxes. That's actually not really the like Wilsonian way of doing it. That turns out not to work very well. But you do something like that. You for example, like one way you could do it would just be to send P to PC from below, although that also doesn't work very well. So there's a lot of art in exactly how you do this. You sort of make the model either finite volume or subcritical in some way, and then you want to understand like how are things changing as you approach the critical points. And in this RG framework, you want to kind of view this as some kind of infinite dimensional dynamical system or something like that. And exactly how you set up like the coordinates for that is, again, there's a lot of art in how you do that. And then ultimately you want to say, actually, this whole thing is behaving, in fact, very much like a finite dimensional dynamical system near like a nice hyperbolic fixed point or something. And then you, if you're into that kind of thing and you went to the right undergrad classes, you're very happy. Many of us are probably still not happy, and we need to go back and read those undergrad textbooks. But in any case, you know, once you've made that reduction to being like a finite dimensional, morally being like a finite dimensional dynamical system around a hyperbolic fixed point, you're kind of in a good place. Now, the trouble with this is, of course, as I said, there are a huge number of decisions one has to make in exactly what one means when setting all of this stuff up. You have to, you know, say, okay, what is the parameter that I'm varying and looking at? You know, what are like good coordinates for the space and so on. And one tends to, you know, ultimately there's this thing, you want to treat it like some kind of finite dimensional dynamical system, roughly speaking, but actually, if you want to really prove that the errors are small, it gets really like hideously technical. So this has been done successfully, like in fully rigorous mathematical works, but not for percolation. So, but for some other models, so for example, there's something called the phi-4 model, which is similar to Ising, and also for weakly self-avoiding walk, it's been done by in a series of works by Bauschmidt, Bridges, and Slade about 10 years ago now. So there are cases where this RG stuff has been made rigorous. It's just very hard. But they're all for models of the form Gaussian free field plus interaction, basically. That's always what they want to. So it's saying like self-avoiding walk is like simple random walk plus interaction, but they always want to be working with like models of fields because that's how they define everything is in terms of the field, basically. And so for models like percolation, it's not known how to do that. Now, the way physicists do it and like where these numbers come from, ultimately, is, well, something that's kind of nonsense, really, but there's probably a way of making sense of it, but it hasn't been done yet, which is that, okay, so there's something called the Potts model. So Q equals, it says, Q is the number of states. Two-state Potts model is the Ising model. You have plus or minus. You know, if you have more states, you have more colors. Anyway, it doesn't really matter what it is exactly, but the Potts model is like more naturally one of these kind of field theories. You could think of it as like some interacting Gauss version of the Gaussian free field. And morally speaking, percolation corresponds to like a one-state Potts model. And so in some sense, I mean, there's the random cluster model. There's actually a way of making sense of that, but it doesn't seem to be the right one for doing stuff like this. And the way these things work is, and then they tend to pass to something else called the phi cube model, but let's not even worry about that. They basically do all the analysis for some other model, like the Potts model, and then at the very end they say, okay, now let's take Q equals 1. The Potts model with only one spin is a completely degenerate thing, so you don't really want to work with that. They do everything with the more states, and then they just say, well, we get an answer, now let's plug in Q equals 1. Now, of course, that's not a good way of reasoning, at least as far as I know. I mean, if someone finds a good way of doing it, then it'll be great. But, you know, we don't know how to make that precise. Now, there was a very similar state of play some years ago with self-avoiding walk, which is that there was this idea that self-avoiding walk is like the phi-4 model, which is a model of a random field with n components, right? So n is like the dimension of the field. That self-avoiding walk was like a phi-4 model with a zero-dimensional field. It's actually very similar kind of heuristic to this percolation thing. Again, it seems like complete nonsense, but in fact, in that case, there was a good way of interpreting this in terms of a supersymmetric version of the phi-4 model where you have fermionic fields and bosonic fields, and they just have to have the same dimensions so that they cancel or something. Anyway, let's not go there. But, you know, so far, nothing like that has been made sense of for percolation. So we really don't know how to get started, which would probably mean turning percolation into an equivalent field theoretic model that you can then run this kind of RG on. I mean, that's sort of the most natural approach to proving the conjecture, although, of course, it would be much nicer to have a more probabilistic approach. Okay. Good. So let me just say one more thing before we finish for today, which is, okay, so what is the state of play with 3, 4, and 5 dimensions? Okay, so I mentioned that in physics the best method they have, at least for these kind of things, like the critical dimension and so on, is this renormalization group approach. And the idea that, well, I guess both of these people had many ideas, but one idea that Wilson and Fisher had was to say, instead of like, okay, so they're studying the Ising model. So for the Ising model, the critical dimension is 4. They said, rather than looking at 3-dimensional Ising, which appears to be very hard, let's study the Ising model in 3.999 dimensions. So they actually have a paper called, I think it's like critical exponents in 3.999 dimensions, something like that. So in other words, you want to work at dc, d is dc minus epsilon. Say, okay, well, the critical dimension is not too bad. Maybe we can understand like perturbatively around it, what's going on. Now, of course, as a mathematician, your first concern is that this doesn't make sense. The dimension is an integer. Your second thought as a mathematician might be, let's do fractals. That's actually a really bad idea. I mean, I think it's interesting to study percolation on fractals, but it's not going to give you the right continuation of this story. In fact, making sense of this is not too bad. It's sort of the least problematic part of this approach in some sense. But anyway, let's just roll with it. So they say, okay, let's suppose we work in very slightly below the critical dimension, and let's try to expand the exponents around their mean field values. Okay, and what they found, what has subsequently been found for percolation, I should say, they didn't consider percolation, is that, for example, delta is 2, so that's its high dimensional value, right? 2 plus 2/7 epsilon plus 565 over 6,174 epsilon squared plus ... Eta is 0 minus 1/21 epsilon minus 206 over 9,261 epsilon squared, etc. And, continue the series. And so a couple of remarks about this. So one thing that you might have noticed if you're paying close attention is that we have 2/7 here and here and 1/21 here and here. That is actually a general phenomenon. So it's a general heuristic phenomenon that the power of the log at the critical dimension becomes the one-sided derivative of the exponents as you go below the critical dimension. So you might find that a reason to care about these log powers if maybe you didn't find them interesting before. Okay, so that's one nice thing. Of course, these are just conjectures, right? And in fact, it's not even clear exactly what the conjecture is. Another thing is that these series, they do not compute them, generally speaking, to infinite order. I mean, these coefficients get very complicated very quickly. They're often, it's difficult to tell what sign they have even and things like that, or if they're 0 or, things like that. It's also, and I should say there are papers, like modern papers in physics that are like computing the coefficient of epsilon to the 4, right? Like you can write a paper just doing that, and there's someone called Gracie who's worked on this quite a lot recently, and if you look at his papers, there are like formulas that take up whole pages and things like that. Anyway, the other thing is that these expansions, they're not expected to converge, right? So they're supposed to have 0 radius of convergence, right? So In other words, what that means is that they are what are called asymptotic expansions, meaning if you cut off the series after any finite number of terms, then the error should be little o of the last term that you kept in. But on the other hand, you're not supposed to be able to just sum them and get a series. You know, there are many ways in mathematics of producing numbers from divergent series. You know, there's like Borel resummation, and you know, many of you will have watched YouTube videos about you know, 1 plus 2 plus 3 or whatever. Although there are a number of ways of extracting finite values from divergent series, and it's believed, I think, that some of these series are not even well behaved enough to do that. They're not even what are called like Borel summable series. So I'm not sure about these ones particularly, but some of the asymptotic series arising in percolation are not supposed to be Borel summable. So it's a little bit unclear how much one should believe these, or like how useful it would even be to know such a thing. But still, it's one of the only approaches we have. And basically, in terms of the difficulties, I would say that they're very similar to this. I mean, especially if, you know, it's not a coincidence that you get the same numbers here. The actual computations you have to do are very similar to get the log corrections or to get the linear term in epsilon here. But the problems for doing this rigorously are very similar. You know, the fact that doing RG at all is difficult, the fact that you have to convert percolation maybe into some field theory before you get started, these are all the same problems at present. I should say that for some models of like spin systems, there are versions of this that actually have been done rigorously, at least to the linear term in epsilon by Gordon's side. Okay, it's probably a good time to finish. I should say I'll pivot at some point more towards doing mathematics rather than physics. But hopefully you enjoyed seeing these conjectures, and thanks for your attention. Yeah.
Were you saying that there are actual results for self-reporting walk?
Like here, you mean? Yeah, so there are results for what's called continuous time weakly self-avoiding walk. So this is the model studied by Bauer-Schmidt, Bridges, and Slide. So this is where you start with a continuous time simple random walk, and then you add in this energetic penalty for self-intersections. This is the model that is, I think there is a version of this known for self-avoiding walk as well, actually, but they have this equivalence between continuous time weakly self-avoiding walk and a certain supersymmetric 5-4 model. As I said, I think there is a version of that for self-avoiding walk as well, but it has some technical things that make it more difficult to study. Of course, once you work with these supersymmetric models, you've left the domain of probability theory, I should say. So you know, they're not probability models anymore. But in that case, they really have proven many things like this about exactly what log corrections are. I think that they have not proven convergence to Brownian motion, if I remember correctly, but I don't know how hard that would be in addition to what they did. Yeah. Well, it's a supersymmetric model. Yeah, I mean, well, okay, I'm really not the right person to tell you about this, but I have read enough introductions of papers and had enough discussion with Roland and Tyler and so on. So basically, you want to formulate things in terms of Gaussian integrals, which have some sort of algebraic structure, right? And then you imagine you can have Gaussians that are taking values in like anti-commuting variables, right? So things that when you you know, when you commute, you get a minus out, right? And or nilpotent variable. There are all these various things, and so you can formulate an integration theory for fermions, right? It's not normal integration. You can has other kinds of algebraic properties. You know, once you can integrate things, you can formulate statistical mechanics, whether or not you're doing probability, right? I mean, when you do quantum mechanics, it's not so different, right? So, you know, once you have this theory of fermionic Gaussian integrals, you can formulate fermionic statistical mechanics, and it's just, okay, you just have to define what these linear operators are, right, that integrate. Usually it's integrate exponentials of things, right? That's usually what you want to do against Gaussians. I would have to go look at the papers to give you a better answer than that, but ultimately it means taking determinants of things, basically, right? I think fermions mean determinants, if you're a mathematician.